Okay, so now I'm going to do number 6 on chapter 7 of HL review. So number 6 basically gives us an equation for the acceleration here. And then for part A, it's asking us to find that the time to slow down the velocity can be shown by this equation right here. So first, in order to do that, we're going to have to get this equation for acceleration in terms of the time. So first we have to get it into velocity and then time. All right, so now we know that the derivative of the velocity is going to be the same as the acceleration. So the equation of the acceleration is right here at the top. And so we're just, instead of saying A equals for that, we're just going to say the derivative of the velocity. And then if you simplify that, you're just going to get negative v squared minus 6400 over 200. And then now we have to write this equation in terms of the time. So if you antiderive just dt, so basically you have to get this side with just dt. So if you multiply both sides by 1 over dv, then you'll get this right here. And so if you, now you're able to isolate the dt and have dv on the opposite side. So now that you have isolated the dt, when you antiderive it, you're gonna get t, which is exactly what we wanted. And then when you antiderive this side right here, you're gonna get 1 over, it'll be like 200 over v squared plus 80 squared. But here it's saying to show that it's 200 times that, which is the same as saying 200 over this entire thing. And then for part B, let's see what it's asking. So for part B, it's asking for I, it's saying explain why acceleration can be expressed as velocity times dv ds, where s is displacement in meters of the body at time t. So it's asking us why A can be accelerated. So we have to show that. And so we know that A is equal to dv over dt, which is the derivative of the velocity. And we know that dv over dt is the same as saying the derivative of velocity over derivative of displacement in terms of derivative of displacement times the derivative of displacement in terms of derivative of time. Because if you multiply this out, the ds's cancel out. So you get dv over dt. But this is the same as saying velocity times the derivative, because this right here, ds over dt, is the velocity. So now you have proven that acceleration is the same as velocity times dv over ds, which is what part I is asking. Then the next part for part B is saying, hence, find a similar integral to show that in part A for distance s traveled as the body slows. So you have to find a similar integral that shows the part A. So we have to find in terms of s, or in terms of displacement this time, using this answer that we got in part I for B. So we know that this now is the same as acceleration, so you can plug that in for acceleration, which is into the acceleration equation. And then you can multiply both sides again by 1 over dv. So in that case, you will just have ds remaining on this side. Then when you antiderive that, that's s, which is the displacement. And then again, you'll get the same thing, which is the antiderivative of 200v over this. But since they want it similar to part A, we just took the 200 out to the front and multiplied to the entire antiderivative. And then for part C. Okay, so part C is asking us to use parts A and B and find the distance traveled and the time taken until the body momentarily comes to rest. So we have to find the distance and the time until it comes to rest, which means that the velocity is going to be 0. So we know that one of the boundaries of the antiderivative has to be 0 because it's coming to a stop. So we're trying to find the amount of distance and the time from 40 to 0. So all we have to do now, because we have the this from part A, we got the equation to find the amount of time has passed. And then from part B, we have the equation to find the amount of displacement or distance that has passed. So all you have to do is plug in 40 and 0 into both of these boundaries. And then when you plug that into your calculator, you can get that the distance is going to be 22.3 and that the time is going to be 1.16 seconds. So that's number 6, A, B, and C.